嗨，你好，我是马克教授。My name is Mark Turcott, and today I will talk to you about classical mechanics. So the topic today is classical mechanics. And we're going to study one of the most important and basic concept in classical mechanics, and it's called simple harmonic motion. Simple harmonic motion refers to a motion that is periodic motion. Typically in simple harmonic motion, the restoring force is directly proportional to the displacement. So to give a few examples, there would be oscillations on a spring, the oscillations of a simple pendulum, and also oscillations or molecular vibrations. So you can see this spans quite a bit of topics here. So the characteristic of the motion is that it is sinusoidal DAL in time. That is, the motion can be described by a cosine or a sine function. It has a single resonant frequency. And as I said before, the net force is proportional to the displacement. Okay. Oh wow. Not very good. Let me see if I can clean that up a little bit. Well, this will have to do for the demo. So a simple harmonic oscillator example would be a mass on a spring. So here's a spring supporting a mass M at the bottom, and the mass is at rest. So you can define an origin of everything by the rest position of the mass. And of course, so this is the equilibrium position of the mass. Of course, if you displace the mass a little bit towards the bottom, then it'll tend to want to go up and down and up and down. So therefore, we're talking about motion up and down about this reference, this origin here, which is the position that the mass naturally takes when the system is at rest. So we're going to call a coordinate x, measuring the distance up or down. So when x is positive, it measures the distance up, and when x is negative, it measures the distance downwards. Mathematically, a restoring force will be a vector which is minus times a constant times the displacement. So the displacement is a vector, it's either up or down. The force is also a vector, but it has this quality that there's a minus sign here. So the force always is opposed to the displacement. If you think about it, it makes perfect sense. If you push the mass up, then the spring is going to tend to push it down. And if you try to extend the mass down from the rest position, then of course the spring is going to try to bring it up. So the force that's acting on the mass is always opposed, opposite the displacement. So the SI units for force are newtons, and the distance is measured by meters, m. Bad choice of let's call this capital M for the mass to avoid confusion. And the units of the so-called the spring constants are Newton per meter. Okay. So this is a little bit messy. So from basic mechanics, force is equal to the mass times acceleration, which is equal to the second derivative with respect to time of the distance. But here everything is measured along the same axis. So you can forget about things being vectors because they're all act upon up and down direction. So using the equation from before, you have m d squared dt squared of x is equal to minus kx. And if we define omega squared is equal to k over m, then d squared dt squared of x is equal to minus omega squared x. This equation is well known in physics, in mathematics, and it has a solution x of t is equal to some constant c1 times cosine omega t plus c2, another constant, times sine omega t. So actually, if I rewrite this above, x of t is equal to c1 cosine omega t plus c2 sine omega t, it turns out that it can be rewritten using a trig identity as a some other constant times cosine omega t minus phi. So these two are the same thing. So obviously the a must be related to the little c's, and So it turns out that A is equal to square root of C1 squared plus C2 squared. And tangent phi is equal to C2 over C1. So these things have a name. A is called the amplitude of motion. Phi is called the phase angle. And we talked before, omega is equal to square root of k over capital M, which is the angular frequency. Which we can define as 2 pi times the regular frequency, f, little f. So little f, the regular frequency, is equal to 1 over 2 pi square root k over capital M. And since the period of the motion is 1 over the frequency, then the period, capital T, is equal to 2 pi root m over k. The period is how long it takes for the mass to return to the same position. If I had more time, I would go through some details, and in a classroom settings, I would proceed as such that I would just do the following. Give some results, and then ask the students to, as an exercise, demonstrate the results. So the first result is that the speed of the mass is equal to omega square root of a squared minus x squared. Okay? And then, never mind how you get that, that's a different question. But we can see that the maximum speed has to be omega times a. Why is that? Because this is minus x squared, so the smallest that x can be is 0. So the maximum speed has to be omega square root of a squared, or omega times a, and it occurs at x is equal to 0. So that's the first result. The second result is that the kinetic energy of the mass is given by 1/2 k times a squared sine squared of omega t minus phi. That's the kinetic energy, how much energy there is in the moving mass. But there's also energy stored in the spring, because when the spring is compressed, there's a lot of energy stored in the spring, and when the spring is not compressed, there's 0 energy. So the potential energy, and we use U of t, turns out to be equal to 1/2 k a squared cosine squared of omega t minus phi. Because these quantities vary with time, each vary with time according to these equations. But interestingly enough, and this is the most important result, is that the total energy, E total, is equal to 1/2 k a squared into sine squared omega t minus phi plus cosine squared of omega t minus phi. And it doesn't matter what the time is, because sine square plus cos square of anything is always equal to 1. So E total is equal to 1/2 k a squared, the total energy in the system. And it is constant with time. It does not change, which is a fundamental result of simple harmonic motion and mechanics. Thank you.